Hi guys, I'm Suraj Manickam and this video is on my industrial DDP titled Designing an Insulin Dosage Algorithm for Safe Insulin Dosing in Type 1 Diabetes Patients. My supervisors for the project were Mr. Himanshu Sinha from IIT Madras and Mr. Praveen from CareOp Solutions. Chapter 1 Motivation.
Type 1 diabetes, the body cannot produce enough insulin on its own, requiring external delivery, which can become a clinical challenge. Meals can cause glucose spikes, insulin acts late, and each patient responds differently. The aim is simply not to bring glucose levels down, but to do it without pushing the level dangerously low, that is below 54 mg per dl. Now, existing systems show that useful automation needs memory, prediction, personalization, and hard safety constraints. For care-of solutions, this motivates an indigenous clinical assistance layer for insulin dosing, eventually tunable for Indian patients.
Chapter 2 Methodology.
Methodologically, this is a simulator first closed loop. Virtual patients and meal days enter the Havorka simulator, which is wrapped as a gymnasium environment for RL training. Havorka was selected because it is compact, interpretable, and still captures delayed glucose insulin dynamics. The agent receives 48 frames of 14 features, 4 hours of glucose, insulin, meal, time, previous action, and patient context. It outputs two actions, basal multiplier and microbolus. The reward encodes a clinical priority, avoid hypoglycemia, reduce hyperglycemia, and discourage erratic insulin delivery. Raw actions are never directly developed. A safety shield clips unsafe actions, suspends insulin during lows, and enforces insulin onboard limits. Finally, PPO with frame stacking gives a simple, stable controller without recurrent network complexity.
Chapter 3 Results.
After hyperparameter tuning and observing that longer training did not improve the safety performance trade off for the final results, I selected the 1.5 million step model as the final one. On 100 held out virtual patient day episodes, the controller achieved 74.88% time in the 70 to 180 range, 92.17 in the broader 70 to 250 range, and a mean glucose of 152.8. Most importantly, it had zero time below 54. Behaviorally, the policy learned smooth basal regulation while using microboluses as the main corrective channel, especially around meals and high glucose periods, aligning to clinical logic. Phase-wise results showed the main weakness. It's still underdosed immediately after meals, especially post-breakfast and post-dinner. But the safety shield intervened only 0.2% of the time, suggesting that the policy had mostly internalized safe action boundaries. Finally, ablations confirmed that the strongest contributors were previous action features, meal information, and temporal history.
Chapter 4 Conclusion. To conclude, I will borrow George Box's line. All models are wrong, but some are useful. Now, we built a modular pipeline containing virtual patients, the Havorka simulator, a history-aware PPO controller, and an explicit safety shield for insulin dosing. The step is to make the model deployable by adding CGM noise realism, testing against real patient data, and comparisons against stronger baselines like MPC. Although this is not a clinically deployable product yet, this is a very strong first step towards one.